Good morning, students. Welcome to video lecturing class on dynamics of machines. Today we'll start with the problems on critical speed or vibration measuring instruments. So the first problem is the statement is a rotor of mass 12 kg is mounted midway on a 25 mm diameter horizontal shaft supported at the end of two bearings. The span between the bearings is 900 mm. Because of some manufacturing defect, the CG of the rotor is 0.02 mm away from the geometric center of the rotor. If the system rotates at 3000 rpm, determine the amplitude of steady state vibrations and dynamic force on the bearings. Take E equal to, that is Young's modulus equal to 200 gigapascal. So first we'll list out the given data. Mass is 12 kg. Diameter of the shaft is 25 mm he has given. So it is 25 into 10 raised to minus 3 meter. Length of the shaft is 900 mm, that is 0.9 meter. Centricity is 0.02 mm, which is equal to 0.02 into 10 raised to minus 3 meter. And he has given the speed as 3000 rpm. And he has given Young's modulus as 200 gigapascal, that is 200 into 10 raised to 9 Newton per meter square. Amplitude you need to calculate, and you need to calculate the dynamic force on each bearing. So here the one thing you need to remember that don't get confused with this problem and the previous problems which you have solved in the last videos. So whenever he says the rotor is mounted on a shaft, if the shaft comes in this statement, that means you make sure that it is a problem on the critical speed only. Okay. So now we have the equation. The steady state amplitude is given by y equal to plus or minus e divided by omega n square by omega minus 1. Or in place of omega n, we can directly substitute nn by n. But we know that the critical speed is given by nn equal to 0.4985 divided by root of delta, where that delta is the static deflection. So for a simply supported load, because here it is mounted on two bearings, so the condition is simply supported beam. So for simply supported beam, the static deflection is given by WL cube divided by 48 EI, where this W is m into G and I is pi by 64 into D raised to 4. Substituting all these values in delta, you will get the static deflection as 4.66 into 10 raised to minus 4 meter. So this is the static deflection. And we have critical speed equal to 0.4985 divided by root of static deflection. Substituting that, you will get the speed as 23.09 rps whenever you are using this equation. So remember that you will get the speed in terms of rps only, that is revolution per second. So now if you convert this one into rpm, it will become 1385.25 rpm. So we have the equation y equal to plus or minus 0.02 into 10 raised to minus 3 divided by nn, that is mg by n minus 1. So if you substitute that, you will get y as 0.0254 into 10 raised to minus 3 meter. Then the second bit is dynamic force on the bearings. So the dynamic force on the bearings is given by Kt into y, where this Kt is the stiffness, that is load per unit deflection. So mg by delta. So already I calculated delta. So substitute that, you will get the stiffness as 25,252,618.03 Newton per meter. To 2,52,618.03 Newton per meter. So the dynamic force will be kT into y you have calculated here. So if you substitute that, you will get it as 6.42 Newton. Then it is mounted on two bearings, so the load on each bearing will be mg by del 2 plus this dynamic force 6.42 divided by 2. So put together it will be 62.07 Newton will be the load on each bearings. So next problem is, the statement is, a rotor having a mass of 5 kg is mounted midway on the 10 mm diameter of shaft supported at the ends of two bearings. The bearing span is 400 mm. Because of certain manufacturing defects, the CG of the disc is 0.02 mm away from the geometric center of the rotor. If the system rotates at 3000 rpm, find the amplitude of steady-state vibration, dynamic force transmitted to the bearings, neglect the damping, take E equal to 1.96 into 10 raised to 11 Newton per meter square. So assume that this shaft is simply supported. So for this, the given data are M equal to 5 kg, D is 10 mm he has given, so it will be 0.01 meter, L is 0.4 meter, and he has given eccentricity as 0.02 mm, and N has 3000 rpm, and the Young's modulus as 1.96 into 10 raised to 11 Newton per meter square. So first we have the equation for steady state amplitude, that is y equal to plus or minus E divided by omega n by omega whole square minus 1, or we can write it as E divided by nn by n whole square minus 1. But we have the equation for nn as 0.4985 divided by root of delta, that is static deflection, and he has given that it is a simply supported beam condition, so delta will be WLQ by 48 EI. Substituting all these values, you will get delta as this, that is 6.798 10 raised to minus 4 meter. So now if you substitute this delta in this equation, so you will get the speed as 19.12 RPS. If you convert that one into meter RPM, you will get it as 1147.20 RPM. Now you can make use of this y equation to calculate the deflection. So here nn is known, n is given, E is given, so substitute all these values, you will get y as 2.34 into 10 raised to minus 5 meter. Now the force transmitted to the bearing can be calculated as, first the dynamic force will be kT into y, where this kT is W by delta and y you have calculated. So substitute all these values, you will get dynamic force as 1.688. Then the load on each bearing he has asked. So this is the total load. So each bearing means half of that one. 1.688 divided by 2 will be 0.844 Newton. Then the total load on each bearing will be mg by 2 plus this load on each bearing. So it will be 25.3237 Newton. Then the third problem is, a disc of 4 kg is mounted midway between the bearings, which may be assumed to be simple supports. The bearing's span is 480 rpm. The steel shaft, which is horizontal, is 9 mm in diameter, and CG of the disc is displaced by 3 mm from the geometric center. The equivalent viscous damping at center of disc may be taken as 49 Newton second per meter. If the shaft rotates at 760 rpm, find maximum stress in this shaft and compare it with the dead load stress in the shaft. Take modulus of elasticity as 2 into 10 raised to 11 Newton per meter square. So here mass of the disc is 4 kg, length is 0.48 meter, and diameter of the shaft is 9 into 10 raised to minus 3 meter. Eccentricity is 3 mm, and he has given damping coefficient as 49 Newton second per meter. and the speed is 760 rpm, and he has given Young's modulus. So now first we'll try to calculate the static deflection, delta equal to WL cube divided by 48 EI. So substituting all these values, where I is pi by 64 into d raised to 4. So you will get the static deflection as 1.4036 into 10 raised to minus 3 meter. Now the stiffness of the spring is given by 48 EI by L cube. Okay. So substitute all these values, you will get KT as 27,956.8 Newton per meter. So it is like KT equal to W by delta only, but delta is 48 WL cube by 48 EI. If you substitute all those values, this delta in that equation, this is the simplified form of that one. Okay. So now the circular frequency of undamped vibration is omega n equal to root of g by delta, where this g is acceleration due to gravity. Substitute that, you will get omega n as 83.6 radian per second. Now we have the equation for critical speed of the shaft also. So NC equal to 0.4985 divided by root of delta. So delta you have calculated. Substitute that, you will get the NC as 13.306 RPS, whereas that NC will be 798.335 RPM. Now the circular frequency of the shaft, that is omega, is 2 pi n by 60. So n he has given it as 760. So you will get omega as 79.6 radian per second. So the frequency ratio will be omega by omega n, which will be 0.952. So here he has given damping coefficient, so you cannot ignore zeta here. So the damping factor zeta equal to C by Cc, where Cc is given by 2m into omega n. So C he has given, m is known, omega n you have calculated. Substitute that, you will get zeta as 0.0733. Now for the critical damping with the air damping, we have the equation y by E equal to omega by omega n square whole square divided by under root of 1 minus omega by omega n whole square plus 2 zeta into omega by omega n whole square, that is r square, 2 zeta r whole square. So now if you substitute all the values, only unknown is going to be y here. So the additional deflection will be 16.18 into 10 raised to minus 3 meter. Then the dynamic load on the bearings FD is given by, in this case, it is a root of ky square plus c omega y whole square. And if I take y as common term, it will be y into k square plus c omega whole square. So in this also, you know all the values, substitute those values, you will get the dynamic load as 456.72 Newton. Then the dead load on the shaft will be m into g. M is 4, g is 9.81, it will be 39.24 Newton. Therefore, the total maximum load on the shaft under the dynamic condition will be Fd plus dead load. So it will be 495.96 Newton. After that, he asked us to compare the stresses also. For that, let us consider the bending equation. M by I equal to sigma by Y equal to E into R. So from this, that is sigma, and from these two, we can write a sigma as M by I into Y, where this Y is D by 2. So for simply supported beam with central load, the maximum bending moment can be written as M equal to F into L by 4. So substitute that, FL by 4 into D by 2, I is pi by 64 into D raised to 4. So in this also we know all the equations, all the terms, only unknown is this F and this sigma. So we will get that sigma in terms of F only. So sigma will be 1676.694 into 10 raised to 3 times of F. So the total maximum stress under the dynamic condition will be sigma max will be 1676.694 into 10 raised to 3. F value is 495.96, which we have calculated here. This value. Okay. So sigma max will be 8.316 into 10 raised to 8 Newton per meter square. And the maximum stress under the dead load. So in that case, in place of F here, we have to substitute only the dead load, that is 39.24 Newton. So if you substitute that, you will get the stress as 6.58 into 10 raised to 7 Newton per meter square. Now moving further, the fourth problem is a vertical shaft 12.5 mm in diameter rotates, is a long bearing and a disc of mass 15 kg attached to the shaft at the midpoint or the span. The span of the shaft between the bearings is 0.5 meter. The mass of the center of the disc is 0.5 mm from the axis of the shaft. Neglecting the mass of the shaft and taking deflection as for the beam fixed at both the ends, determine the critical speed of rotation. Also determine the range of speed in which the stress in the shaft due to bending will exceed 125 megapascal. Take E as 200 gigapascal. So here he has given diameter, mass he has given, length he has given, eccentricity he has given, sigma value he has given as 125 megapascal, that is 125 into 10 raised to 6 Newton per meter square, and E as 200 into 10 raised to 9 Newton per meter square. Now in the statement he has given one condition that the both ends are fixed. So for a beam fixed at both the ends with a central load, we can write the static deflection equation as from the BOM WL cube divided by 192 EI. So in this also we know all the values. Substitute them, we'll get delta as, that is static deflection, as 4 into 10 raised to minus 4 meter. Now the critical speed NC is given by NC equal to 0.4985 divided by delta, root of delta. Substitute that, you will get NC as 24.93 RPS. So if you convert that one into RPM, just multiply with 60, you will get it as 1496.07 RPM. So from the fundamental equation of the bending moment, we have M by I equal to sigma by Y, where Y is D by 2. So for a beam fixed at both the ends, the maximum bending moment is given by W1L by 8. So now substitute in place of M as W1 by L, W1L by 8. So the only unknown is going to be in this equation is W1. So we will get this W1 as 383.5 Newton as the additional load due to the centrifugal force. Now for 15 into 9.81 Newton, deflection is 4.10 raised to minus 4 meter. For this much load, that is 383.5 Newton load, what is the deflection he has asked. So Y equal to, in place of load, you substitute 383.5 into 4 into 10 raised to minus 4 divided by 15 into 9.81. So we will get Y as 1.043 into 10 raised to minus 3 meters. So that is going to be the additional deflection due to centrifugal force. So now we have the amplitude equation as Y equal to plus or minus E divided by omega n by omega whole square minus 1. So here you need to determine the speed here. So in terms of speed, it will be NC by N. So in this equation, only unknown is going to be N, because NC already have calculated. So if you substitute that, you will get N as 1230.02 RPM and one more another n as 2073.45 rpm. That is, once you have to take with the plus sign and once you have to take with the minus sign, so that you will get the two values of n. So the range of speed at which the stress will exceed 125 megapascal is 1230.02 rpm to 2073.45 rpm. So here, while calculating these things, the only thing you need to take care is, this is for the dead load. The deflection is, that is static deflection, is 4 into 10 raised to minus 4 meter. Okay. So similarly, here he has asked us to calculate what will be the deflection for this additional centrifugal force. So in place of that additional load, you have to substitute this value to get the value of y here. Okay. And for calculating the range of the speed, once you take this with plus sign and once you have to take with the minus sign. Then moving further, the following data relate to a shaft held in long bearings. Length of the shaft is 1.2 meter. Diameter of shaft is 14 mm. Mass of rotor at the midpoint is 16 kg. Eccentricity of center of mass is 0.4 mm. E is 200 gigapascal. Permissible stress in the shaft material is 70 into 10 raised to 6 Newton per meter square. That is 70 megapascal. Determine critical speed of the shaft and the range of speed over which it is unsafe to run the shaft. So neglect mass of the shaft. So first we'll try to list out the given data. So that is L he has given, D he has given, M he has given, E he has given, and the Young's modulus he has given, sigma he has given. So he has us to calculate the critical speed NC. So for critical speed we have the equation NC equal to 0.4985 divided by root of delta. So as the shaft is very long here, it may be assumed to be fixed at both the ends. So for that condition, the delta value, static deflection, is mg L cube divided by 192 EI. So here we know all these values. So with the help of those values, we can calculate delta as 0.0037456 meter. So now if you substitute that in NC equation, you will get NC as 8.145 RPS, which in terms of RPM it is 488.7 RPM. Now you have to calculate the range of speed. So to calculate the range of speed, let us consider a bending moment. M by I equal to sigma divided by Y, where Y is B by 2. So for fixed beam, the bending moment is W1 L divided by 8. So substitute that in this equation. So only unknown is going to be W1 there. So W1 will be 125.718 Newton is the additional load due to the centrifugal force. Now for that you need to calculate additional deflection. So for W equal to M into G, that is 16 into 9.81 Newton, this is the deflection. And for W1 equal to 125.7 Newton, what is the deflection? Just cross multiplication. So this into this divided by this. If you write that one, you will get Y as 0.003 meter. But we know that for the deflection, we have the equation as plus or minus E divided by NC by N whole square minus 1. So from this, you can calculate the range of the speed. Once you take Y with plus sign and once you take Y with negative sign, so that we will get the range of speed as N as 459 RPM and the next speed is 525 RPM. So the range of speed which is unsafe to run the shaft is from 459 RPM and 525 RPM. So this last statement you have to write because it is asked in the statement, question statement. Then moving further, we are having, this is the problem on vibration measuring instrument. So here the statement is a vibrometer having the amplitude of vibration of machine parts as 4 mm and zeta as 0.2 performs the harmonic motion. If the difference between maximum and minimum recorded value is 10 mm, determine the natural frequency of the vibrometer if the frequency of the vibration part is 12 radian per second. So here he has given zeta as 0.2, omega as 12 radian per second, and the amplitude of vibration of the machine parts as B as 4 mm. Okay, and Z is nothing but he has given that the maximum difference is 10 mm. So from here to here it is 10 mm, but while taking the amplitude you have to take only half of this one, so it is 5 mm, and R is omega by omega n. So we have the equation for the measuring instruments as Z by B equal to, or in some of the textbook is given it as Z by Y. Okay, so Z by B equal to R square divided by root of 1 minus R square whole square plus 2 zeta R whole square. So in this equation we know the value of Z, we know the value of B, and we know the value of zeta. Okay, so only unknown is going to be R. So solve for R this equation so that you will get R as 2.12, where this R is omega by omega n. From this you will get omega n as omega by R, which is equal to 12 divided by 2.12, that is 5.66 radian per second. So we'll end the session here itself. So if you have any doubt, you can leave the comment in the comment box. Thank you.